In this video, I provide two examples of hypothesis tests with a single data set. I don't work through the technical details of calculating your test statistics and your p-values, so it is assumed that that's already understood. Instead, I will provide a fairly lengthy discussion of data and data sets and variables and the sorts of information that you have as a brief lesson on what sorts of tests are appropriate for a given data set and what sorts of tests aren't appropriate. In our data here, we have two variables about sales. So this is some sort of numbers of sales for a business sort of situation. And we have a variable here in column D called July training, which is apparently qualitative. It takes on two values, yes and no. And it's meant to represent whether or not some optional training occurred. Now, from just this information, it's not clear whether this value of June sales is somehow matching or paired with this value from August sales. It's possible that this is 14 randomly selected stores. This is a different 14 randomly selected stores. So it would make sense to calculate the average level of sales in August and compare that to the average level of sales in June to decide which is larger. However, it isn't necessarily clear to look at this row and say that in August sales were 16 units higher, because you don't necessarily know that these two values came from the same store. Now that's sort of implied by this training variable that is suggesting that this particular observation, or the second observation, got some training, so this was probably a value of sales before that training happened and a value after. But still, you need to be a little bit careful here that maybe this isn't 14 randomly selected stores that either did or didn't have training. Now, if you were told that observation 2, all three of these values, correspond to the same item, like the same person or the same store, that would be helpful. And that would allow you to do some different tests. Alternatively, if you had another variable like this that provides the name of maybe a particular sales associate, that gives you some sort of indication that this level of June sales is representing the sales that corresponds to a particular person. This is the sales in August for that particular person, and this is indicating that that person got that optional training in the month of July. That means that we know that these 14 observations here came from a specific 14 people, named over here, and these 14 observations came from the exact same people, and they haven't been shuffled or resorted. Now that allows us to do some different types of tests than we would be able to do if we didn't have that column A. For example, if we wanted to know if August sales were larger than June sales, we could just take the average of these, take the average of these, and do a two-sample test to see whether the mean in August is equal to the mean in June. If we wanted to know things like, did individuals sell more in August than they did in June, instead we would say, well, here we've got an observation in June of 67, here we have 83. What we really have there is one observation of growth that tells us that Joe sold 16 more units in August than he did in June. That's some indication that sales increased. For Jim, however, sales decreased by 3. For James, sales increased by 10. And we could create a new variable here, maybe in column E, called differences or growth or something like that. And then we could ask questions like, was growth positive? Or maybe we could subsample the observations and say, for people who got the training, did sales increase? Or maybe was sales growth different for people who got the training versus sales growth for people who did not get the training? There's lots of different questions we could ask. And we could certainly ask hypotheses about individual variables. These would be one-sample tests. Like we could make a claim about the proportion of people that got training. Maybe it's 15% or 50%, or maybe it's 90%, something like that. And we could certainly make claims about the level of June sales, things like does the average person sell 70 units in June? Now the two tests that I'm going to propose here that you are welcome to replicate yourself. So pause the video, copy down the data set, and then carry out these tests yourself. I'm not going to go through the details of the test. I'm just going to jump straight to the solutions and focus on the proper language and the presentation of critical values, p-values, and illustrations that show what the test is doing. So I propose we look at the July training variable, and because this is qualitative, we can only do proportions tests. We might ask, do at least 2/3 or 66.7% of our sales associates choose the training? Note there that our population is going to be all associates, and we only have information for apparently associates whose first names start with J. Maybe this is store J, one particular store, and we want to make some claim about all stores, and to save money when we are collecting data, we only looked at one particular location. For no particular reason, I'm going to say use the critical value approach, and when I present my answers, I use a significance level of alpha equals 0.02. For the second test, I'm going to propose a two-sample test, and as I said earlier, there's a couple of different tests that we can do now that we have paired data. I am going to do a particular paired test. So the question that I want to ask is, did associates that received the training, so I'm only looking at the 10 associates that have yeses in column D, did their sales change? I'm not saying anything about whether they increased or decreased. I'm just asking whether or not they're different. For that test, we're going to use the p-value approach. I use a significance level of 0.05, although changing that wouldn't affect the way you conduct the test. And as a warning, to calculate that p-value, you're going to need to use the t-distribution, and t-tables don't allow you to calculate p-values accurately, so you're going to need to use Excel, and I recommend the function t-dist, and you'll have to work through that yourself. And one more time, if you want to replicate these results yourself, pause the video, and I'm going to reveal the solutions right now. Okay, so remember that for our first test, we're asking about a proportion. I claimed that the true proportion for all sales associates that would choose to opt into the optional training is 2/3. So our null hypothesis then, really the alternative is the one that you should be thinking about first. If I want to know that at least 2/3 opt into the training, then you want to put that in the alternative hypothesis so that you can confidently say that the true proportion, using the symbol pi, is greater than 2/3 or 0.66666 repeating. To be able to confidently say that, you want to reject the plausibility that the true proportion is less than or equal to 0.6666. So that thing that you want to reject is what you put into the null hypothesis. Again, we've got a significance level of 0.02 that I picked for no particular reason. And then I went to the z-table, because the proportions test is a z-test, and I found a critical value that has 2% in this upper tail. That's the pink or red area up here. That level of z is 2.054. Notice that for this one-tailed test, the tail has to be in the upper range, because the alternative that would cause you to reject the null hypothesis is large values of those proportions. And here are results. Based on our sample of 14 observations, we found that 10 out of the 14, which is about 71%, said yes, which is slightly above the null hypothesis of 2/3. However, based on standard errors and some formulas that we used, the z statistic is only 0.378, which is not very far away from the null hypothesis level of 0.67. And then our conclusion then is, because our sample proportion of 71.43% of the 14 observations, it's only 0.378 standard errors away from the claim, which is not very many standard errors. compared to our threshold or our limit of 2.054. Therefore, we cannot reject the null hypothesis that the true proportion might be something less than 2/3. It might be 0.66, it might be 0.65. For all we know, it might be 60% or even 50%. Because our sample proportion was only slightly above that, our evidence is not conclusive enough to say that that null hypothesis is false. Now our second test, I said that our data allows us to do a paired t-test. We're going to restrict it to only the 10 observations that said yes to the optional training. And we wanted to know if the effect of that training caused their sales to change. And the way to phrase that null hypothesis isn't so much about the mean in June versus the mean in August, although technically that's the same claim. Really what we're looking at here is a single sample of 10 changes in growth between June and August. So we can phrase that as a null hypothesis that the mean of all the differences, the population mean, is equal to 0. And because we're only interested in whether or not the training had an effect, either positive or negative, our alternative hypothesis is two-tailed with a not equal sign. And for alpha equals 0.05, that means our rejection region looks like this. So we've got the 2.5% of the smallest values and the 2.5% of the largest values. For 10 observation of differences, this is a t-test with 9 degrees of freedom. So instead of labeling this x-axis here with z, we label it as t, and I use the subscript 9 to indicate the number of degrees of freedom. And our results of the 10 observations of changes in sales, we have a mean of the differences, something like x bar, we're going to call it d bar for the averages of the differences, of an increase of 3.9 between June and August. And with some standard deviations and some standard errors, that corresponds to a t-statistic of 2.415, which is shown right here in blue. And the probability or the p-value of being beyond 2.415, looked up from a t distribution in Excel, is about 2% or 0.019, about 1.9%. And because our rejection zone is two-tailed, the p-value also needs to be two-tailed, so we take that blue area right here and we double it, and then it ends up looking like this. And we say that about 3.893% of the time, that's the blue area, we see observations that have t-statistics or that are 2.415 standard errors away from what you expect. And that's quite a few standard errors, and that 3.893% is a relatively small probability, relatively small being less than 5%. We say that if the null is true, we observe something relatively unlikely or relatively rare, happens only about 3.9% of the time. And because that's rare for our standards, we say, well, either we just observe something that's rare if the null hypothesis is true, or perhaps the null hypothesis is false. There's no judgment call here. We reject the null hypothesis because we observed something relatively unlikely, and we say that the training does have some sort of effect, either positive or negative. Our data suggests that it's probably an increase in sales, but because of the way we set up our test, the proper conclusion is just to say that we can reject the null hypothesis that the training had no effect, and conclude that the training did have some effect on sales.